Hello everyone, welcome to today's webinar. I'm Alexandra Taylor, Assistant Editor for CNEN, and I will be moderating today's event. This webinar is titled Seeing is Believing, In Situ Correlative Raman's SEM, and is being sponsored by Protochips. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you're disconnected during the webcast, please log in again according to the instructions you received earlier. You are encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNEN Online after the live webcast. This presentation today is being sponsored by Protochips. Protochips works to enable researchers who need to observe their samples in situ in liquid or gas environments at atomic or near-atomic resolution to transcend the limitations of the TEM, STEM vacuum environment and provide systems for dynamic observations. We will hear today from Jordan Mooring, Marketing Communications Manager for Protochips. Jordan earned his PhD in Materials Science and Engineering and now works with Protochips' marketing and product development team to explore new opportunities for in-situ tools and solutions. During the presentation, we will also hear from Dr. Sergey Prokhodo, who is an Associate Adjunct Professor in the Department of Materials Science and Engineering at the University of California, Los Angeles. Sergey has experience in the structural characterization of materials using advanced microscopic and spectroscopic techniques. I will now hand over to Jordan.
Okay, thanks Alexandra for that kind introduction, and good morning to everyone around the world tuning in. It's great to have you, and I think you'll really enjoy some of the results and presentation stuff we've got lined up for you today. So as she mentioned, my name is Jordan Mooring, and I work at Protochips, a company that specializes in tools, workflows, and solutions primarily focused on in situ microscopy. Now, some of you may be familiar with our products for transmission electron microscopy, or TEM, but today we'll be talking a little bit more about our SEM products. But to get started, I wanted to go over some in situ techniques in a little more detail for those of you who may not be terribly familiar with this burgeoning and rapidly growing field. So what is in situ and why should you be using it? Well, the word in situ is Latin for in place, and in the context of electron microscopy, it simply refers to manipulating or controlling a sample within the microscope. So this can be anything from mechanically loading the sample to heating it up to applying some sort of external bias or even changing the environment surrounding the sample itself. Now, the reason that in situ experimental control is so valuable is that it allows you to see real-world dynamic reactions and processes in unprecedented detail. So by controlling the sample in situ, you're able to decrease the time to results since you're essentially imaging your sample under real-world conditions. And you're able to do this by extending the capabilities of your microscope. In essence, in situ turns any microscope into a nanoscale reaction chamber. So as I mentioned, Protochips serves the in situ community. And what I wanted to do is just briefly give an overview of some of our products for those of you who may be familiar with broader electron microscopy techniques. So in 2009, we introduced the first commercial liquid cell holder for TEM or STEM called Poseidon Select, which allows you to image liquids safely within the TEM. Now, as you can see, we've seen a lot of folks using Poseidon Select to study batteries, biological materials, liquids, emulsions, for applications ranging from material science and oil and gas to life science and soft materials. One of the other products we offer is Atmosphere, which allows you to expose your samples to pressurized gases up to 1 atmosphere of pressure and up to temperatures of 1,000 degrees C. All of this is done within the safe confines of the TEM, and we find that this type of in situ research is particularly useful to the catalyst community who need to study nano-sized materials under hot, corrosive environments like those found in the catalytic converter. Now, our third product is the one that we'll focus on today, and we call it Fusion. We call it that because it combines precise electrical biasing capabilities with accurate temperature control, allowing you to have unprecedented control of the excited state of your sample. Now, in situ heating tends to be sort of the bread and butter of most in situ researchers. So we see a lot of scientists using it to study batteries, metals, semiconductors, insulators, to study electrical devices, but also to do more fundamental materials characterization of the structural, chemical, crystallographic, and morphological state of their samples. So essentially, anyone that's using SEM to characterize their materials tends to be the type of folks that we see looking for in situ heating and other types of sample biases. So on the left, you can see our Fusion TEM holders, which I want to use to explain sort of how the system works. The SEM stage, as we'll see in a moment, is virtually identical, but I find that the TEM sort of stage is a little bit easier to understand. So Fusion uses MEMS-based chips to control the sample. And for me, this is the really cool part. If you know anything about in situ microscopy, you know that MEMS technology has really transformed and sort of changed the paradigm of what in situ can do. And it's really thanks to this MEMS technology. So to use Fusion, you simply put your sample on one of our MEMS-based E-chips. They feature a really durable electron transparent sample support, which is made of an amorphous silicon nitride membrane. The integrated circuits inside the E-chip are used for heating and electrical biasing. So once your sample is placed on the chip, it can be loaded directly into the holder where the electrical pins automatically align themselves with the contacts on the chip. And one of the really great parts about the system is that there's a ton of different varieties of these chips. So you can pick the best one that works for your experiment or your research. And so as I mentioned, what I'm showing here is our TEM holder, but the SEM stage is assembled in a very similar way. So Fusion itself features several components that all work seamlessly together to synergistically within your SEM. So once assembled, the E-chip and Fusion stage pair are loaded into the SEM sample stage. The electrical connections on the stage are connected via included cable to the port plate that is mounted to the side of the SEM. Now, that's all done to get the electrical circuits and connections to be outside the SEM. So externally, Fusion is powered by a Keithley power supply that is controlled by our workflow-driven Clarity software. We spent a lot of time on our software to make it really easy to use. And so you can pretty much get up to speed on in situ in just about 15 minutes using this software. So whether you're looking at particles or films or fib samples or just other small things in the SEM, Fusion allows you to control your sample via all of these components working together to turn your SEM into an in situ reaction chamber. But this is really just how it's assembled. And I wanted to talk just briefly about what kind of things you can do with this system. So for one, Fusion heats and cools really fast. So it can reach temperatures up to 1200 degrees C in just over 1 millisecond. So this is perfect for studying ultra-fast phase transformations like martensitic phase transformations, but you can also do liquid melting and solidifying all within the microscope. So here you can see a copper-silver particle, which is solidified from its molten state almost instantaneously. In the solid state, you might be able to make out some of the crystal facets on the surface of the particle, and that gives us indication that it's at the solid state. And obviously, in the molten state, you can see sort of thermal fluctuations showing the molten particle moving around. But you're not just limited to very fast heating and very fast cooling rates. You can also control the heating and cooling rates to whatever rates you desire. So here you can see the temperature of a glass frit sample being increased just a few degrees Celsius per second until the glass begins melting at its liquidus temperature, which is about 650 degrees C. So obviously, thermal and heating studies are really important for in situ microscopy, but fusion, as I mentioned earlier, can also be used for electrical studies. So the precise electrical connections between the chip and the holder, all integrated through the Keithley power supply and Clarity software, allow you to deliver nanoamp currents to your sample with just a few clicks of a button. So, for example, one of our collaborators at Joel was studying the failure of gold electrical traces. So in the microscope, they were able to apply a 14 milliamp current across the sample. And they were able to characterize the post-mortem structure of the sample using electron backscatter diffraction and secondary electron imaging, which you can see here. So they used EBSD, or electron backscatter diffraction, to map the crystallographic changes across the sample, which you can see shown here. Now, it turns out that these crystallographic transformations were a manifestation of the electrical properties of this gold trace, and they were able to iterate on this sample and improve its functionality later on. And I think this study is a perfect example of some of the power of in situ techniques. You're able to combine the experiment and characterization steps of your experiment into one single microscopy session. So you're able to accelerate your research by obtaining better quantitative results faster, since you're able to do all of this type of characterization and sample control instantaneously. So for me, really the question is, why wouldn't you want to use in situ? We've seen researchers and scientists all around the world in disciplines ranging from material to life sciences that are using in situ techniques every day to improve their research efforts and accelerate the time to results. So that's really it for me. I hope that this overview helped everyone kind of get up to speed on fusion and how it works. You'll definitely want to stay tuned, though, because the next part of the presentation is going to be the really cool part. Sergey and his team have done some really cool work using our fusion heating stage combined with the power of in situ Raman. And so I'll go ahead and pass it over to him and let him explain to you guys some of the stuff that he did. So the floor is yours, Sergey.
Thank you, Jordan. Thank you, Alessandra. Hello, everybody. And I would like to thank organizers of this webinar, first of all, Protochips, which bring together specialists in the area of in situ experimental studies. And I'm excited with given opportunity to share some of our recent results on integrated SEM Raman systems we use, and some experiments which incorporate heating stage fusion from Protochips, which we use on the SEM platform. Well, in my talk, I'll try to give short introduction to Raman spectroscopy and explain why we would like to incorporate Raman system with the SEM, as well as what would be the benefit of using the SEM Raman integrated systems when we can add heating capabilities to such arrangements. Well, the Raman effect was discovered back in 1928 by Professor C. Raman, and light-based technique When monochromatic light shines into material, we can get elastic Rayleigh and non-elastic Raman scattering of light. Some photons set lattice mode vibrating, some photons change their energy. Energy change depend on masses of atom vibrating, nature of chemical bond, physical effects on chemical bonding such as stress, crystallinity, and intensity of scattering depends on number of molecules present. In other words, this technique is quantitative. While generally, Raman spectroscopy is sensitive to the chemical bond type of material, and everything that somehow affects bond can be studied with Raman. That is why the following information can be received from Raman spectroscopy. First of all, it allows to determine the chemical compound or formula by presence or absence of specific peaks on the spectrum, and we call it fingerprint technique. It is important that characteristic Raman frequencies or peak position are representative not just for the chemical compound of material, but also its crystalline form. For instance, between different minerals form of titanium dioxide. Raman can distinguish which one of three different mineral forms was probed, for example, anatase, bruchite, or rutile. Raman also sensitive to stress-strain state of the materials, and that can be determined by change of frequency of Raman peak. In other words, shift of the position in the peak representative to the stress-strain state of the material. Then polarization of Raman peak is representative for the crystal symmetry and orientation and can be measured by the change of the peak intensity, its height. We also can rate crystal quality or amount of plastic deformation, which can be determined by width of the Raman peak. And the amount of materials can be determined by intensity of the Raman peak, while also temperature can be measured by observing so-called stocks and anti-stocks of the Raman peaks. So it's quite powerful technique. And however, among the strengths of Raman spectroscopy, we should probably mention that it is non-destructive. Well, generally considered non-destructive technique. It allows flexible sampling, any phase, any size, no special preparation is needed. It can probe materials through the light and transparent medium, such as glass or water, that works for biosamples in their natural environment. And it can be used with fiber optic, which means that the signal can be transferred on a big distance. For the weaknesses of Raman, we can probably mention that its Raman effect is very weak. So it means that it requires time to collect the signal, and for instance, when we need to perform mapping of imaging of the material, it might take a long time. A partial solution can be found with using streamline mapping. However, it's not completely satisfy researchers. One of the possible solutions might be to couple Raman with SEM, which basically provide with instant imaging. Well, another problem is that spatial resolution, because it's light-based technique, it's limited by the wavelengths of the light, according to Rayleigh criteria, and partial solution also can be fulfilled by use high numerical aperture lenses or shorter wavelength sources. However, it's still not completely satisfying. This problem also can be solved by coupling Raman with SEM. We know that scanning electron microscopy can provide nanometers resolution. Well, we can add to this that the intensity of Raman response for particular compounds depend on the excitation wavelengths of laser use. That means that to get Raman response from a particular compound, we need to use specific excitation. there is a general trend that organic materials have strong response when red or infrared lasers excitation used, whereas inorganic has better response with green or blue lasers. That means that for given Raman system, you are not guaranteed that you always get a proper response. Sometimes you have to check your materials using different excitation to find which one works best with your material, and it means that specific type of studies on different materials require different type of excitations, and you are lucky if you have all these capabilities in one system. Well, why we would like to integrate Raman with the SEM? Well, partially it's clear from previous slide. SEM is also non-destructive technique to analyze and study morphology and topography of sample surface with high spatial resolution up to few nanometers. Then SEM EDS system coupling of the SEM with energy dispersive and wavelength dispersive spectroscopy is very common those days, and those provide elemental composition of your materials. So basically, SEM and EDS can provide elemental chemical analysis of materials. Also, with SEM, we know that we can study crystallography by coupling SEM with electron backscattered and diffraction attachments. Well, integration of Raman with SEM EDS bypasses limitation of Raman standing alone. The speed and spatial resolution can be improved, and on the top, it adds Raman capabilities to entire system. However, such integration is not flawless. The biggest difficulty is due to the fact that SEM is an electron beam-based technique, whereas Raman is light-based. Bringing the light to the SEM and collecting the weak Raman response from materials is very complicated technically, and it is not always simple to use. That means that in majority of experiments, we probably don't need to integrate, we don't need the integrated systems, and it is probably easier to use two different systems standing alone. Nevertheless, we can outline three major areas of analysis when integrated SEM EDS Raman system are indispensable. First of all, when the size of analyzed feature is a few micron or smaller, it is hard to identify the feature with optical microscope, which is traditional platform for the Raman. Then, surface-enhanced Raman scattering can be employed within the SEM chamber for characterization of materials. And the third area is when dynamic studies may be necessarily under variable conditions such as temperature and pressure. SEM temperature stages with different design are currently commercially available, as well as alternating pressure systems through use of variable pressure or environmental SEM are also available those days. Well, this slide shows the in-view Raman spectrometer from Renishaw, which we have on traditional optical platform. We got the system interfaced with variable pressure field emission gun SEM Nova 230 from Thermo Fisher Scientific, and SEM coupled with NORAN 7 EDS system, also from Thermo Fisher. In such integration, laser beam signal can be brought to the SEM by using fiber optics through the structural and chemical analyzer. And on the top, we can see there is fiber optic coming out from the system. But generally, the system can be used on optical platform when we don't need such integration. The next slide shows structural chemical analyzer directly attached to the SEM chamber. and EDS detector right behind the column, which is not seen on this image. The next slide shows the SEM infrared camera image of the inside of the SEM chamber with the pole piece of the SEM, Raman probe when it is introduced inside the chamber, and the standard SEM sample stage. And when we apply the system with fusion heating stage from protochips, this slide shows that the bracket of the heating stage can be replaced instead of standard SEM stage basically in few minutes. On this, here we can see secondary electron image, SEM image of the heating stage platform with the sample deposited. The heating area, the heated area is approximately 150 by 150 micrometers, which is right in the middle of the E-chip. Well, to demonstrate the potentials of the SEM Raman integrated system, I would like to start with some of our results recently published in Journal of Archaeological Science. That was a study of the 12th century wall painting done in collaboration with Professor Iana Kokoli from Kotzen Institute of Archaeology at UCLA. The image A on the left shows the enclaster of Sant Neophytos in Cyprus with context of the cliff and facade of the enclaster. Image B shows the detail of the wall painting in the naos depicting the enthroned Christ dated to late 12th century. With his left hand, he is holding the Gospel book, and the arrow indicates the location where a microsample, few microns, was taken. And image C shows the optical microscope image of cross-section of the paint fragment showing the stratigraphy of the painting. From top surface, we can see the dark brownish layer, most likely alteration of cinnabar, which is mercury sulfate. Next, the intense red layer, most likely cinnabar, with some presence of hematite, probably, and an orange light brown layer, mostly presented with hematite. And at the very bottom, we can see plaster layer. The white square on the image C shows position of the sample which was imaged, the area which was imaged in the SEM, which is shown on the next slide. On this slide, we can see the polished fragment of the paint sample with the plaster layer. A is an optical microscope image. On B, we can see backscattered electron image of the same area as shown on A. And on C, we can see secondary electron image, high magnification image of inclusion, which is marked with error on the image A and B. The same inclusion can be also identified on some EDS map shown on two lower panel. Optical image shows that stratigraphy of the painting with followed layers. The most easily to recognize and see is bright red color cinnabar, and it shows a high concentration of mercury and sulfur, which is quite consistent. We also see some inclusions which are rich with calcium, oxygen, magnesium, and silicon, and specifically we see some inclusions which are rich with magnesium and silicon. It was kind of first suggestion that it might be asbestos, and by the way, we can clearly see that on optical image, it is very hard or practically impossible to see this individual inclusion, whereas on the image B, this inclusion can be seen quite well. And high magnification, high resolution image shows fibrous structure morphology of inclusion, which is also suggests that it might be asbestos. How even with such strong evidence, it was kind of brave for us to suggest that the asbestos, since the use of asbestos in manufacture of cements and plaster was thought to be a novelty of late 19th century, and we're dealing with artifact which was 12th century. Raman spectroscopy, here we see results taken with Raman, can give an ambiguous answer. Raman spectra number 1 and 2 are taken from two different inclusions rich with magnesium and silicon. Those spectra are compared to a reference asbestos chrysotile sample, confirming that our inclusions which are magnesium and silicon rich is indeed chrysotile. In this example, we can see that the SEM can give a great spatial resolution of the feature of interest, and it gives elemental analysis of the feature. With those two results, we can suggest that feature is asbestos. However, we cannot 100% be sure unless we prove it with Raman and distinguish specific crystalline form of asbestos from 6 other naturally observed. Such discovery is of big anthropological significance since it helped to understand better ancient economics, the trade routes, and interaction of ancient communities. This discovery offers a new clue that can be used to correlate the technical data with stylistic analysis in classification of paintings. And up to the recent time, we knew there were few applications of asbestos in the past as fire-resistant fabrics for oil lamps, wicks, and some ceramic were made with adding asbestos. However, it was not reported industrial use in building construction, like in this case with plaster. Asbestos was not used until late 19th century when it was produced on industrial scales. In my second example on use of integrated SEM Raman system, I'll show you the approach we use for the organic dyes identification on ancient textiles. This study was performed in collaboration also with Professor Kakoli, I mentioned in previous study, and also former conservator from Los Angeles County Museum, Dr. Diana Rambaldi. The identification of dye in ancient textiles provide a major analytical challenge. Usually high-performance liquid chromatography coupled with mass spectrometry is the most common technique for identification of dyed moleculars. However, this technique has limitation in study of ancient dyes due to the fact that it applies a destructive protocol, and it requires a relatively large amount of material, of sample. Raman spectroscopy could be a feasible solution. However, due to very small amount of dye materials, use of Raman signal is very hard to measure. Surface-enhanced Raman signal technique can be considered as a powerful extension of Raman spectroscopy. It was discovered that the Raman response can be significantly enhanced up to, say, 8 orders of magnitude and higher in the presence of some metal nanoparticles deposited directly on the surface of the analyte. However, difficulty with SERS analysis is that it's hard to provide required good contact between the analyte and metal nanoparticles to excite the plasmon, which is responsible for the strong Raman response. Due to that reason, the SERS results are often not very consistent. And in this study, we were able to measure dye stuff molecule on individual fibers. This experiment required deposition of silver nanoparticles on single fiber segment, about size of 5 millimeters, and such analysis was not destructive, though of course it was invasive. We used two different fibers from the museum collection dyed with red-pink dye. One sample was alpaca fiber dyed with cochineal, widely used in South and Central America since ancient time. The main coloring matter for cochineal is carminic acid. Another fiber, also red in color, was dyed with Indian madder. Madder dye stuff is also red colorant with main coloring material alizarin and purpurine. On this slide, we can see the alpaca fiber fragment with deposited silver nanoparticles. Silver nanoparticles were deposited from colloidal solution. And it is obvious that nanoparticle distribution is not uniform on the fiber. That can explain why it is hard to expect good consistency with SERS result measurements when they are performed on the optical platform. And image C is optical image, and it is hard to see where you get a good layer of nanoparticles. SEM allows to select areas on the fiber where silver nanoparticles nice and uniform layer. Then SERS analysis can be directly carried out without necessity of moving the sample. This slide shows results of SERS analysis on the wool fiber dyed with shea root. The analysis of areas with thick layer of nanoparticles or without nanoparticles resulted in low signal-to-noise ratio or no signal at all. Areas with thin layer of silver nanoparticles led to optimal reproducible spectra characteristic of the dye moleculars. And observed bands on the experimental sample at 1153, 1290, 1316, 1457 and 1617 are in good agreement with reference sample of alizarin, the main chemical compound of the shea root, and in compliance with earlier published results on the SERS of alizarin. The analysis of areas with thick layer, and this slide shows that sometimes layer of nanoparticles can be thick or it can be detached. It also produces no Raman response. There is no signal, and only uniform area provides good Raman response from the material. So this slide shows result on SERS analysis of alpaca fiber dyed with cochineal. The spectra of experimental sample shows characteristic bands specific, which is similar to what observed on the reference sample for carminic acid. And it is in agreement with published result for the SERS analysis of cochineal. The results clearly illustrate the potential of this non-destructive approach for the identification of different organic colorants. Utilizing the high-resolution imaging of the SEM, it is easy to locate areas on the deposition, areas of the thin deposition of silver nanoparticle, enabling successful and reproducible SERS analysis and correct identification of the dye stuff. It is also possible to identify the species of the fiber based on morphology, and SEM quite powerful for that, more powerful than, say, optical microscope. In my next example of using integrated SEM Raman system, I would like to demonstrate its power when it's used with heating stage, enabling the study of phase transformation. We used the fusion heating stage from prototypes, and the sample was calcium carbonate sample of few micron deposited directly on prototype platform. The thermal decomposition of calcium carbonate plays a role in several geologic processes and has important technological application. The reaction follows the equation which is shown on the slide. The slide shows in situ SEM secondary electron images of the calcite crystal before on A, during B, D, and after heating experiment C. Multiple cracks formation shown with arrows and surface wrinkle due to the loss of carbon dioxide become visible at 900 centigrades. The next slide shows Raman results on calcite sample under the heating. Sample was slowly heated from the room temperature up to 900 centigrades. On A, we can see Raman spectra of the crystal before and after transformation, and B, C, D shows Raman spectra of the crystal during the in situ heating experiment. Spectral area of characteristic calcite peaks at on slide B, we can see characteristic calcite peaks at 153, 280, 711, and 1085. Those are visible at 200 centigrades. 153 nanometers peak disappeared at 600. All peaks disappeared at 900 centigrades due to the sample glow. That's kind of a problem to get Raman system signal. And on the image C and D, we can see vicinity of 280 and 1085 peaks shown, which are shown with higher zoom. And on this high zoom specters, we can see slight shift of the peaks, and we also can see the split of the peak at this 280 peak. In my last example, I would like to show some of our results that demonstrate capability of prototype heating stage for in situ SEM study of material morphology when the SEM system was used alone without a Raman unit, but with the heating stage. The study was on coarsening of the inverse opal structures of Cerea zirconia. This study was performed by our former PhD student Daniela Casillas, who worked in a group of Professor Bruce Dunn, and currently Daniela is process engineer at Intel. The objective of this project was to predict and quantify the high temperature behavior of Cerea zirconia inverse opal for the use in thermochemical hydrogen production. Particular interest was on high temperature behavior of materials and how the material degrades at high temperature. Using in situ SEM setting with from prototype heating stage, we were able to directly monitor the degradation of the structure at high temperature and also find an empirical relationship between the grain size of Cerea and window size of inverse opal. This slide shows result on inverse opal morphology change with increase of the temperature. Preliminary data suggests that non-template Cerea has higher surface area, but in terms of propane conversion, inverse opal perform much better, which shown on the chart. At this chart, we can see relatively low temperatures. There is an improvement in fuel conversion efficiency for inverse opal. And those measurements only carried out up to 500 centigrades. Well, this is known data, which was known before this experiment was started by Daniela. However, biggest interest was for us, for Daniela, to see how the structure behave at much higher temperature, which basically expected to give much better efficiency of conversion. And the temperature we were needed was 1200 centigrades. However, cycling at this temperature can degrade structure quite significantly. The question remains, how long do Syria inverse opal keep ordered porosity under this operating condition, and how to relate microstructure change to a microscopic feature growth. This slide shows set of SEM secondary electron images taken at elevated temperature 1100 centigrades. Total time of experiment was 15 hours, and images shows that some wall gets thinner. We get change of the windows on the Syria, so generally we can observe clear degradation of the structure at this temperature. Well, I would like to return to this slide. So the structure of inverse opal was deposited directly on the prototype platform surface. The sample was imaged with low heating and at 100 centigrades per minute. All images were taken using accelerating voltage 10 kV. And the images clearly indicate that since time the structure undergone significant degradation. Beside in situ SEM experiments, there were some ex situ experiments on measurement of the grain size change with heating. And those results were combined with these in situ results and allows to derive this empirical equation. The formula allows for prediction of microscopic behavior of inverse opal lifetime based on the easily obtained ex situ measurements such as, say, XRD for grain size measurement. So by measuring of the grain size, we can predict what happened to the window of the opal structure, which basically critically responsible for the coefficient of conversion. Well, in summary, I would like to make several conclusions. First of all, that commercially available integrated SEM EDS Raman systems are feasible and indispensable for defined range of scientific experiments. Fusion heating stage from prototypes can be successfully incorporated with SEM, EDS, and Raman integrated systems. Such incorporation opens unlimited capabilities for in situ temperature and pressure-dependent studies of physical and chemical characteristics of materials on a single platform that combines the individual capabilities of the SEM, Raman, and EDS. And finally, capabilities of integrated SEM, EDS, Raman system exceed what can be achieved when each instrument is used independently. Thank you for your attention.
All right, thank you so much, Sergey. And now we can move on to the Q&A portion. So our first question, there are 4 electrodes on the biasing chip. What's the difference between them, and which 2 are connected to the outer circuit?
Yeah, so this is Jordan. I can take that. So I think this question was about the sample I showed that was on the electrical chip. So you can do several things. One, you can just do a 2-point measurement using the outer electrodes, or you can lay a sample across all 4 and do a 4-point probe measurement. But we also offer a ton of different variations of those E-chip electrical configurations. So those were just a few that I showed, but all 4 electrical circuits can be used on any of our chips.
What is the temperature range in which the in situ SEM chip can work?
Yeah, I think I mentioned this briefly in my presentation, but you can heat up to 1200 degrees C with the system. And I think I mentioned the heating and cooling rates that were accessible with that as well. But yeah, hot enough to melt a lot of things. So 1200 C is what we can go to.
How about the contamination of carbon? Can that influence the Raman spectrum, and can that be avoided in the SEM Raman system?
Well, obviously, everything which contaminate your sample will be reflected on your Raman signal. So because Raman sensitive to any material or compound which add to the surface of your sample. So you have to be very careful to keep it clean. But generally, there is no problem. It's like any sample, when you put it in the SEM, you care about how clean it is, and you try not to contaminate it. So contamination can be serious issue. You just simply not measure signal from your material. You measure signal from contaminant. But generally, it's kind of handled. It can be handled nicely, especially in SEM.
Yeah, and I just wanted to follow up on that. Your carbon contamination is certainly a function of your beam dose. So in TEM, you can see some carbon contamination, and we've done some tests doing EDS in the TEM. But as Sergey mentioned, there's a lot of tips and tricks out there on how to minimize and mitigate the carbon contamination when you're doing this type of microscopy.
Hi, where can I find publications that use this system?
Yeah, that's a good question. So we've actually put together a really extensive interactive bibliography of every publication that has ever used any protochip system. So if you go to protochip.com/bibliographies, you can search around and find all kinds of good articles that have been peer-reviewed and published using this system.
How can I make sure that the light is focused on the particle that I'm interested in under SEM?
Yeah, that's one of the kind of technical difficulty, because you have to calibrate it well. You have to because generally you get video signal from your sample as well, and you can see. On video camera, you can see your laser beam. You can see image of the sample, which is optical image, not very extremely high quality, but obviously can give you sense of good focusing. So if your focusing is not good, you just simply don't get the signal. But generally, if your image focused well, which automatically provide that the laser beam is also focused on the surface. That's something we just simply require some practice.
Can the chiral form of Raman optical activity be determined via this hybrid technique?
Say it again, please.
Can the chiral form of Raman and then parenthetically optical activity be determined via this hybrid technique?
I'm not sure that I understand the question.
Okay. We can move on unless you want to jump in, Jordan.
Yeah, I think they're asking about the just measuring the chirality. I think you're the Raman expert here, Sergey, so we can just move on. Maybe the individual who asked that can follow up and ask it again.
All right. What are the requirements for adding a heating chip in an existing SEM?
Yeah. So our SEM systems work with all of the major microscope manufacturers. So if you have an SEM, you're pretty well set to use the Fusion system. Obviously, you can reach out to us for any specific questions, but the requirements are that the SEM works and that you've got a port plate that's free on the side. Other than that, make Fusion pretty inclusive so that it works no matter your experimental configuration.
Is it possible to do EDX while heating up?
Yeah, this is a question we get asked a lot. So with EDS, the detectors themselves are sensitive to sort of infrared fluorescence. So we've done some experiments at elevated temperatures, at I think 500 or 600 degrees C. When you start going above that, you start getting a really strong fluorescent signal that's not really indicative of the elemental characters of your elements. So yeah, we recommend doing EDS at lower temperatures, but we have seen some customers go up to higher temperatures. There is an effect though.
How does the software work?
Yeah, so the software, as I mentioned in my sort of component of the presentation, it basically runs the whole experiment. So the software, in terms of functionality, is pretty straightforward. It walks you through the experiment. The very first step is to calibrate the chips, which we do internally and in-house. So each chip comes with a custom calibration file that's guaranteed to produce the temperatures and electrical controls that you want. So the software identifies all of the calibrations and calibrates the system for that. But then it kind of walks you through your experiment. It's, what heating rates do you want? What temperatures do you want? Do you want to do waveforms? Do you want to do ramp rates? It's pretty much any control that you want is built into that Clarity software suite. And that's the same software that we use for all of our products. But like I said, we try to make it really simple to use so that you can just run your experiment the first try every time.
Is it possible to integrate TEM and Raman?
Some people do that.
Yeah.
Yes, they were. I don't remember names, but a couple of years ago at Microscopy and Microanalysis, there were a presentation. I think there were a group from Berkeley. They did with Renishaw. They tried to incorporate Raman in the TEM. So there might be some proceeding. I'm sure it should be in some proceeding somewhere like a couple of years ago.
For the SERS measurement, how deep into the sample does the laser probe?
Well, this is light-based technique, and it can go through transparent objects quite deep. It can shine through the glass, so it really, it's just like light. But generally, this is really surface signal, like for opaque objects.
How should you deal with exothermic reactions?
Yeah, I can take this question. So it depends on, I guess, what you mean by deal with exothermic reactions. We've seen individuals that essentially did thermite reactions inside the TEM, so it's definitely not a problem to do exothermic reactions. The only hiccup that we sometimes ask about is how do you control the temperature during exothermic reactions? And for that reason, we actually built into our software a closed-loop temperature control system that can be turned on to automatically monitor and maintain a given temperature. So obviously, if you have an exothermic reaction, there's a lot of heat that's released. And you can set it up so that Clarity detects that change in temperature, decreases the current across our heating membrane so that the temperature is maintained. Or you can, just run it as a normal heating membrane so that exothermic energy is just added to the system. But it's definitely not a problem to do exothermic reactions in the microscope. But I hope that answers that question.
All right, last question. What are some common applications that use in situ heating in the SEM?
Yeah, so I tried to mention a few in my presentation. Obviously, a lot of what Sergey is doing is some some pretty cool kind of forensic microscopy. But as I said, in situ heating tends to be the bread and a lot of materials characterization. So material science applications ranging from batteries to semiconductors to two-dimensional materials, nanoparticles, nucleation and growth, phase transformations, all of those tend to be conducive to heating or electrical biasing, and I'd say those are the main applications that we see interest in.
All right, that's all the time we have. Thank you again, Sergey and Jordan, for your fascinating presentation, and thank you, participants, for being a great audience. Be sure to check CNEN or CNEN Online for information on the next edition of CNEN webinars. Thank you to On24 for technology and production services, and thank you, Protochips, for the sponsorship that made this interactive webcast possible. For CNEN webinars, I'm Alexandra Taylor. Goodbye.
Thanks.
Thanks.